Lesson 1.5, Modeling and Solving Problems with Polynomial Functions. In this lesson, you will be using some type of graphing technology. What I'm going to be using for this lesson is an online graphing calculator I just discovered and I really like. It's called Desmos.com. So if you go to Desmos.com, it takes you one click and you get to their calculator, or you can type in /calculator. Either way, in the workbook, there also are instructions for using a TI-83, and you're certainly welcome to use that, but I do find the online graphing calculator a little bit easier. So let's take a look at the get started piece here. It says this graph represents the path of a ball kicked into the air. What was the maximum height of the ball? So maximum height, there we go, maximum height here, really, if you take a look at the two axes, vertical distance versus horizontal distance, height is going to be a measurement of vertical distance and where is it highest. So I guess that would be the vertex. That'd be the highest point that ball went, and it seems to me it's about 12 meters. So I would write 12 meters here. How far had the ball traveled horizontally when it reached this height? So now we're looking at the horizontal distance here. So if I drew a line straight down, it seems to me it'd be about halfway between these two ticks. The 4, 8, 12, the multiples of 4 are measured. That would be a 10 here, so perhaps that'd be 9. So let's go with 9 meters. And if I look at the entire graph as well, 12, 14, 16, this would be 18. And there's a symmetry to this, right? It looks like a parabola, so 9 is half of 18, so it kind of makes sense that it would be 9 meters. What total horizontal distance did the ball travel? Oh, I just looked at that, and I think it's 18 meters. So it's really just about warming up about looking at graphs. One little application is this is a little bit different than we often graph in physics, because typically when we graph a distance, we usually have time on the other one. So this is vertical distance versus horizontal distance. So this actually looks like the path that the ball went through the air, as opposed to a typical position versus time graph where you get fooled into thinking that was the path. But that doesn't have to do with our course. Let's take a look at the Constructor Understanding. Okay, so the first piece, it says use graphing technology. So like I said, if you want to use a graphing calculator, you can. So you can use a TI device, whether it's 83 or 84. If you would really like to use one of those calculators, you can come and see me. I think we have some in the library. You have to give a deposit, and you can use it for the semester. Otherwise, I really like this Desmos.com. Another online one that works really well is GeoGebra. You can mention that one to me as well, or you can ask me about that one. I can show you that one as well. But lately I've been trying out this one. So let's read this and see if we can convert it into something that we can put on a graphing calculator or graphing software. A certain airline's regulations state that the sum of the length, width, and depth of a piece of carry-on luggage must not exceed 100 meters. Okay, well, let's just take that sentence here and let's see if we can kind of turn that into some math notation on the side here. So sum means the result of addition. So we're going to be adding together a length, so I'll just put an L for length, plus the width, plus the depth. And then it says of a piece of carry-on luggage, so L is going to be the length of the luggage and W will be the width and so on, must not exceed 100 centimeters. Must not exceed. So it could be equal to 100 and it could be less than 100. So we would be putting this inequality sign 100. Okay, so to be fair, I really should be saying let L equal the length of a piece of luggage in centimeters. I'm kind of taking a shortcut here. Several models of carry-on luggage have length 10 centimeters greater than their depth. Okay, so let's take this piece here and convert that into math notation. The length, L, is, and there's no is in there, but it's kind of implied, and is an equal sign. Okay, 10 greater than their depth. So usually when we say 10 less than or 10 greater than, we switch the order around. So I'm going to say to be 10 greater than the depth, that'd be D plus 10. And to be honest, it doesn't matter if we could put 10 plus d instead of d plus 10, but when it says less than their depth, if it was 10 less than their depth, we would have to make sure we said d minus 10. If we said 10 minus d, we'd get the opposite, right? So I'm just going to get into the habit of putting the plus 10 afterwards. Now it says write a polynomial function to represent the volume of this luggage and graph the function. So it's telling me that I should be able to make one polynomial function to graph this entire thing. So I should be able to say something about volume here. Volume. So volume I know is equal to the length. If it's a rectangular solid, like a carry-on luggage should be, it's going to be length times width times depth. But here's the thing: if I'm going to graph this, I only want one variable, right? So which one is defined in terms of the other ones? And I think it's going to be the depth, right? So if I'm gonna write v is equal to, instead of length, I can write 9 plus d plus 10. So d plus 10. Oh, a little messy there. Let's leave the width for a second, and then I got d. Okay, so what I did is I used this information from, I'll call this one equation number 2. This is inequality number 1. So I got 1 and then 2. I used this information to substitute it in here. So how am I going to put w, replace the w with an expression in terms of d? I only want to use d. Well, going back to this one, I can first of all say, oh, I got an L here, so I can change this L here to d plus 10. So I could say d plus 10 plus w plus d is going to be less than or equal to 100. Now I want to represent the volume of the luggage. D plus 10 plus w plus d is going to be less than or equal to 100. If I solve for w now, I would get w plus 2d plus 10 is less than or equal to 100. So now w, if I subtract those from both sides, I'm kind of running out of room here, w is going to be equal to, or less than or equal to, 9d minus 2d, like that. So what I'm going to do is where I see the w, I'm going to put 90 minus 2d. Now you might notice I'm replacing the less than or equal to the full expression 90 minus 2d. In other words, I'm making the width as large as it is possible. To the nearest cubic centimeter, what is the maximum possible volume of this luggage? So I'm going to make the width very large. So I'm making it 90 minus 2d. What assumptions did you make? So I guess one assumption that I made is that I want to use that full 100. I'm going to make the width as large as it can. Okay, so what this polynomial does is if I play around with what d value is, if I make the d larger, then the length and the width have to be smaller. If I make the d smaller, then the length and the width can be a bit larger. So how can I play around with the 3 dimensions of this luggage to get the largest possible? Just to make this a bit more friendly, to make it look a bit more like something we would normally graph, instead of using the d, I'm going to make an x. Something like this, 90 minus 2x, and then an x. So this is an expression of volume in terms of x. In this case, x represents the depth. All right, so let's go and see if we can graph that. If I can get over to my calculator. There we are. There's my calculator. So to just introduce to how it works, desmos.com/calculator. And right in here, I'm going to start writing my expression. So I'm going to go x. And I don't have to say times. I can just go left parentheses. It's kind of neat. It starts graphing it for me right away. A little warning symbol saying you got to write more. X times x plus 10. Right parentheses, and then left parentheses, and then 90 minus 2x, right parentheses. Okay, so when I do that, I'm looking at this, it looks a lot like a vertical line. So I think the problem is one of scale. So I'm using the the wheel on my mouse to scale back. And scale back, and it's looking pretty funny, isn't it? So I think, okay. It looks to me like it's, I need to change my Y scale by a lot, but my X scale not so much, right? So if I go to graph settings, I'll change my X-axis to say, looking at this graph, I don't know, from minus 20 up to plus 50. And now my y-axis should be quite large. I don't know, maybe I'll make it 1,000, or this is the minus part, right? Negative 500 up to 1,000. How's that looking? Oh, I can't quite see where it comes down. Maybe I'll make it up to, what if I go 10,000? Still, what if I say up to 50,000? Oh, there we go. That works a little bit better. And instead of minus 500, I think I might want to go minus 1,000. Oh, maybe 5,000. And now if I remove this, oh, okay, that's looking pretty good. So, and I'm going to go click off to the side to get this. All right, so with a little bit of work, I got my scale about right. And this is a function of that polynomial. This is this polynomial graph. So as the depth changes, this is what happens to the volume. Now we got to be careful a little bit interpreting this value. Like here the line's going below. It's going into the negative. So really, can you have a negative volume? No, that doesn't make sense. All right. The other part is we need to restrict our domain. In other words, there are some values for the depth that don't work. The depth, the width, and the length all have to be positive values. They can't be negative and they can't be 0. So that means that our first value x has to be greater than 0. So that's why we can't have these negative values as well. Because of the second term, I'm thinking that x has to be greater than or equal to 10. No, sorry. Can't be less than negative 10. Makes sense. Now, this 90 minus 2x, here, if I can write on here, the 90 minus 2x is kind of our important one. There we go. So the 90 minus 2x has to be positive. So in other words, it has to be greater than or equal to 0. So minus 2x has to be greater than equal to minus 90. When I divide both sides by negative 2, I have to remember to change the sign of my inequality. So x has to be less than or equal to 45. Why is that the case? Because this piece here, I think it was the width. Is that where it came from? Otherwise, my width would be less than 0. If x is 45, then the width would be 0, and that's a nonsensical one. So it has to be less than or equal to 45. And look, that's what happens right here. So this is the piece here. So we have to have a positive volume, and each of our dimensions have to be a positive value as well. So really our domain here is restricted between 0 and 45, just because of the real world situation. The maximum value here, now here's a nice thing about this. If I just click on this, it gives me our value, and it naturally selects either the positive or the local maximum or minimum or the intercept. So it tells me where the intercepts are. This was right at 45. So the x value is going to be 28.58. So when the depth is 28.58, the maximum volume is 36,210 centimeters cubed. Okay, let's switch over to our piece over here. And do they show us a solution for this? Let's click on Show Solutions. Okay, so they do the same thing with the graphing calculator. They get a very similar kind of function here. It looks like this. And notice they have to do the same scaling that we did, but it's a bit more cumbersome on the TID3, but they get it to work. And there's our answer. Was that the same as what we had? Let's just see. 36,209. 36,210. Interesting how decimals rounded it off, and TID3 gave us more decimals. So the depth of the luggage is approximately 28.6, and then they figure out the other dimensions from that. Okay, hide the solutions here. Think further. In the problem above, suppose the sum of the length, width, and depth was halved. Would the maximum volume also be halved? If the sum of the length, width, and depth were halved, in other words, if they all had to add up to 50 instead of up to 100, then it says here, no, the maximum volume would be much less than 1/2 the original maximum volume because each dimension would be approximately half. Since the dimensions are multiplied, this would result in a volume of approximately 1/8. Okay, they're taking a little bit of a shortcut, but I think that the point that they're making here, I want to write on it again, is since the volume involves the 3 dimensions, length times width times height, right? If we were to divide each of these by 2, or if we were to multiply each of these dimensions times 1/2, so I'm saying times 1/2, if we were to make each of these half of what they originally were, what kind of effect would that have on the volume? Well, if I was to make the length half as much, then the volume as a result would be half as much. If I were to also make the width half as much, then the volume would be half as much because of the length, half as much of the width, and then just by extension, same thing for height. So the combined effect of multiplying the right-hand side by 1/2 3 times would be multiplying by 1/2 cubed, right? Which is the same thing as 1/8. So that's what they're saying here. The function would be more like 1/8. All right, I think we only have 2 examples. I'm hoping this isn't going to take too long today. First example is using the graph of a cubic function to solve a problem. In this case, this is making a box out of either a piece of cardboard or a piece of paper or a sheet metal. You're definitely going to be seeing this style of question many times. A piece of sheet metal 25 centimeters long and 18 centimeters wide is used to make a box with no lid. Equal squares of side length x centimeters are cut from the corners and the sides are folded up. If I go to the second page here, I think there's a nice diagram. Oops. Yeah, so here is an example of the diagram. So here is the sheet metal to begin with. It's 25 centimeters long and 18 centimeters. And in the question, they are, I'm going to go back and so I can write on it. They punch out this corner. So this corner comes out and so on. They take out these corners here. So imagine if you were to remove that. And those little squares, the little red x's, have a dimension of x by x. That's their variable. That's what we're going to play with. Okay. So if you can imagine where the dashed line is, then this is a flap that you would fold upwards. And this one you would fold upwards, and so on. So you're going to have an open box. So this is like the before you folded it, and this is viewing from on top. This is after you folded it, and it's kind of given a more 3D look. So this height here, this height x here is from each side of this square that you punched out. Okay, I hope that makes sense. So if you're going to look at this new box here, again, the volume is going to be the length times the width times the height. The height dimension is definitely going to be x. That's straightforward because that's the x that we punched out. The length and the width, you have to pay careful attention, but you're going to see this pattern over and over again. The original length was 25 centimeters, right? So from all the way to the edge here to all the way to the edge here is 25 centimeters. Now, if we've punched out an x, if we've cut out an x from each side, the length of the base of the box now is going to be 25 minus 2x. So that's where that comes from. It's because if this entire line is 25, then the line from here to here, this will be our new one, which would be, that's the one that's 25 minus 2x. Okay, not 25 minus x because you're going to be taking an x out of each side. Similarly, the width will be 18 minus 2x. So here you got 18 minus 2x. So the volume of the box is x times 18 minus 2x times 25 minus 2x. Then the next part of the solution is they say, well, the question says, write a polynomial. And the next one is graph it. Okay, so using a graphing calculator, you put that one in. The dimensions of the box have to be positive. So if the dimensions of the box have to be positive, this one has to be positive. This one here, 18 minus 2x, has to be greater than or equal to 0. So similarly, minus 2x has to be greater than or equal to negative 18. So in other words, x has to be less than or equal to 9, just like we did before. So that's the important piece here. So the domain is x needs to be between 0 and 9. Because in here, x has to be positive, has to be greater than 0. Here, x has to be less than or equal to 9. Oh, I guess it can't be exactly 9, because if it was exactly 9, this would be 0 again. So here, I should erase, I'm going to squiggle those out. I should erase that. And it shouldn't be less than or equal to 9, it should just be less than 9. So here's my domain of all the possible x values that we can have. Once they've graphed it, and again, it's a little bit of effort to get the scale of the x and the y. I think you can anticipate the x values that you want to graph, because you know it has to be between 0 and 9. So you could just say 0 and 10. I think that's what they've done here. And then the y scale they've entered is 1,000. Now, so with the pardon me, with the graphing calculator, or with whatever online like desmos.com, you would probably have to play with it until it looks about right. Scrolling down, what they need to do on the TI-83, you can read this yourself, is do a trace until you get to the top, and they get a volume of 693 cubic centimeters. This occurs when each square that is cut out has a side length of 3.4. Where do they get that from? That's what the x value is. So this dot here, the x value, you can read it down here, is 3.4, and the y value is 693. So that's my x value. So they can calculate the 3 dimensions. The height was our x value. Our width was 18 minus 2x. So they put in 3.4 for x, and they calculate the width, and our length was 25 minus 2, and then therefore they get the length. Okay, so what I'd like you to do then, I'm just going to back up. I will hide these solutions. I want you to try the very similar question here for your check your understanding, and then I'm going to stop the video, and I would like you to work on the check your understanding, and then I'll come back and show you a solution for it. Okay.